Students, so welcome back to our online session of digital signal processing and application class. In today's session we are going to discuss the concept which we left in the Chebyshev type 1 and type 2. So basically what is the Chebyshev approximation technique, students? The Chebyshev approximation technique is used to perform by using the Iir filtration, right? What is the Iir filtration is all about? It is impulse invariant response that is going to use LPF and HPF. What is LPF stands for? Low pass filter, and HPF stands for high pass filter. So what is the LPF is all about? We know that LPF consists of it allow the lower component and it will resist the higher component. If you had HPF, it allow the higher component frequency and it will resist the lower component frequency. Similarly, in the same manner, we are going to proceed with the Chebyshev approximation. In Chebyshev approximation, the basic idea of Chebyshev approximation is about how do we design the analysis filter. So to design the analysis filter, we should know that the error functions. So now we are proceeding with the first part, that is the type 1. In the type 1 approximation, the error function is selected such that the magnitude response is equi-ripple, means it should have the same ripples in all the kind of bands consisting of pass band and the stop band. So basic thing of the pass band and stop band is about their magnitude response. As we can see in the graph, we do have AP, right? What is AP is all about? It is about 1 by root of 1 plus sigma square. What is this sigma square is all about? It is about taking the value in one direction with x-axis and with y-axis. Let us see the details in the further clarification. So likewise students, so we can write it down that error function. So basically what is the error function of that particular amplitude? We can write it as h of j omega mod of that whole square is equals to 1 plus epsilon square with cn square omega by omega c. What is this omega is all about? It's nothing but the analog frequency, right? So analog frequency by critical frequency is a type 1. Clear? So if you are getting this kind of graph where only I am considering the low pass filter LPF, then I can say this is my type 1. What about the type 2 students? Type 2 would be like this. As you can see here, what is I am just writing? The approximation techniques where the error function is selected such that the magnitude response is equi-ripple in the stop band and monotonic in pass band. It quite reverses that of the previous type 1. So in the previous type 1 what we said, it only have the equal ripples, right? Whatever the ripples you just want to see, those ripples are equi. That means the magnitude response is equi-ripple in the pass band and monotonic in the stop band. If you take a reverse of this kind of response, that could be considered as the what Chebyshev type 2. Similarly, we are writing for the type 2 in this way. Clear? So that's why we can write it down the response of type 2. So here I have mentioned, now just want to find the characteristics of Chebyshev type 1 filters. How do we characterize the magnitude of h mod of j omega oscillation between 1 and 1 by 1 plus sigma square, sorry epsilon square. If I want to find that is the pass band, then I can able to find its equal ripples filters. You just have to see the theory of it. We're mostly concerned with the numericals. How do we obtain the numericals, right? So that is our main concern. But before that, you should know what is the definition of Chebyshev type 1 and type 2. Both the things, you should have to be aware of it and you can able to find out the solution for that particular analysis as well. Clear? So here we do have that magnitude response of that one. It is a monotonic outside the pass band. And the cutoff frequency omega c for that type 2 will be magnitude response that has a value of 1 by root of 1 plus epsilon square, right? The Chebyshev type 1 filters are called as all pole design filter with large value of n order. And how do we find the order basically? That is our more concern. So we will see that also. How do we design that? That is our main concern, main concept of designing, right? To design, the first step is to find their order, right? What is the order here? In the previous method, when we see the approximation technique, which approximation techniques we just learned, students? So we have learned about your Butterworth approximation, right? Here in Chebyshev approximation, what we are seeing, we just want to see the order of the filter. How do you obtain the order of the filter? Same formula, n is equals to, here instead of log we will use cos h in inverse. That's only the difference. Cos h inverse of same factor, 1 by as square minus 1 by 1 by ap square minus 1 whole power 1 by 2 by cos h inverse of frequency in the stop band by frequency in the pass band. Clear? That is the first step. Next thing, we just have to see what is this, whether n value after substituting all the values is even or odd. If n is even, then same, pi is equals to k is equals to 1 to n by 2 bk by sn square plus bk s of n plus ck. That's the h of sn. If your n is odd, then how do we obtain that? H of sn is equals to b naught sn plus c naught pi of k is equals to 1 to n minus 1 by 2. We can substitute and we can write the same factor. What is bk over here, students? In the previous condition also we take bk, right? Sine of 2k minus 1 by 2n. But here we will use 2y of n. That is one extra factor, y of n, right? Admittance function. The y of n, how do we obtain? By using the relation of ck. So bk and ck, these are the coefficients we should know, students. First we have to use this bk value and ck value. In order to get this 2bk and ck, we should know y of n. So basically y of n, how do we obtain? Y of n we can obtain by using this relation. 1 by 2, 1 by epsilon square plus 1 whole power 1 by 2. That is root of 1 by epsilon square plus 1 plus 1 by epsilon whole power 1 by n. Minus the same factor with minus 1 by n. The meaning is that we should know epsilon value first, then we can substitute y of n, then we can substitute c naught at the y of n, we can find bk and ck. It's the reverse. First we should know epsilon. After getting epsilon, we can substitute here y of n. After getting y of n, we can find bk and ck. This is all the kind of relation we should know in order to find out the Chebyshev approximation. Clear? So this is the way we can obtain. For odd values of n, we can find bk such that h of 0 is equals to 1. It is a normal practice where we can use b0, b1, so on till bk all are equal. That is the normal practice, students. So when we do have the next step, after getting what h of s, we have to use a critical frequency, right? So the omega c, how do we obtain for omega c? We have learned in your Butterworth approximation that when is low pass filter, s by omega c. When high pass filter, omega c by s. The same scenario I am using here. Find the unnormalized transfer function with h of s by using h of sn, where sn give rise to s by omega c, right? What is omega c? That is nothing but the omega p. Critical frequency is nothing but the pass band frequency. We can substitute that, and we can substitute in the given condition of h of s, we can able to find all the relation. After getting that, we need to find the step 5, right, students? What is the step 5? Compute the h of s at either by using a bilinear or by using the impulse invariant. We know the bilinear, right? Wherever s is there, we can substitute and we can find 2 by t 1 minus z power minus 1 by 1 plus z power minus 1. We can substitute that, we can able to find by using bilinear or impulse invariant. How do we obtain the impulse invariant? The same factor 1 by s plus p give rise to 1 by 1 minus e power minus p of t into z power minus 1. These two methods we can use it, and we can realize the structures. We know the realization of structure, right? By using direct form 1 and direct form 2. If they ask to find the verification also for designing that particular part, we can able to find that by using z is equals to e power j omega, right? So we can substitute that factor and we can able to design that particular filter by using the Chebyshev type 1 as well as the Chebyshev type. Let us see one problem, students. Design the Chebyshev filter. Design Chebyshev IIR low pass filter using bilinear transformation by taking t is equals to 1 second to satisfy the following specifications. So that is our main concern. That is our main criteria. So if you had those the things, we can able to find and we can able to substitute all the answers. Clear? So students, we do have IIR LPF by using bilinear transformation with the value of t is equals to 1 second, and we can able to find this parameter. So let us see the continuation. Chebyshev digital IIR LPF low pass filter using bilinear transformation by taking t is equals to 1 second to satisfy the following specification. For that, what we'll write? We'll write pass band ripples, delta p is less than or equals to 1.9 dB, and stop band attenuation alpha is greater than or equals to 13.95 decibel, right? Pass band edge frequency 0.2 pi radians per sample, right? We have to convert into omega p. This is that is given. Then stop band edge frequency omega s is given. So what we will do, students? We have decibel, right? We have to convert it into normal form. So what we will do? 10 power that given value. So we got AP and we got AS, right? It is also the value we find. Next thing is what we need to consider. We need to consider its omega p, right? It is in radian per sample. If you substitute that given value in terms of 2 by t tan omega p by 2, 2 by t tan omega s by 2, we can write that given specification in terms of what? In terms of our angular frequency omega p and omega s. We substituted both the values, and next thing we can find the order of the filter. How to find the order of the filter, students? That can be obtained. N is equals to cos h inverse of 1 by as square minus 1 by 1 by ap square minus 1 whole power 1 by 2 by cos h inverse of omega s by omega p. So what is the value of this 1 by as square minus 1? If you substitute, it will be 24. By 1 by as ap square minus 1, if you do it, it will be 0.56. If you take root of that, it will be 6.55. Cos h inverse of 6.55 divided by cos h inverse of 1.717. If you do both the things, we can got it as 2.26. So what is the n value? N should be greater than or equals to 2.26. That is equals to approximately equals to 3. Right? So 3 is what? It's an odd number. Right? So what is the odd number data function we can write? We can determine normalized transfer function h of s when n is odd. What is this? B naught Sn plus C naught. K is equals to 1 to n minus 1 by 2. Bk by Sn square plus Bk Sn plus Ck. We can substitute this kind of parameters. And then epsilon, how do we get epsilon? If you substitute the value of epsilon, we can get this formula, right? 1 by ap square minus 1. If you do it, we got this particular answer. Clear? That is 0.75. Now we need to find yn, right? How do we get yn? 1 by 2, 1 by epsilon square. That is this epsilon, 0.75 square plus 1. The same thing if I'll put it in minus 1 by 3 and plus 1 by 3. I can substitute this given parameters. I can find yn, that is equals to c naught, right? So we found c naught value. After getting c naught, what is the next thing? We have to find ck, right? What is ck value? Yn square plus cos square of 2k minus 1 by 2n of pi. What is n value we do have? N we have as 3, right? 2 3s are 6. So what is yn we had? This is the yn, right? Yn c naught, both are equal. That is 0.375 whole square plus cos square of pi by 6. If you do, you will got it as 0.89. Then bk we can write 2yn sine 2k minus 1 by 2n of pi. So 2n, we had this n value yn, we substituted sine of 2k. K is 2 3 are 6 minus 1, 5. So if you put k is 1, so 2 1 are 2, 2 1 is 1 is 1 only. So 2 into 1 minus 1, that is 2 1 are 2 minus 1 is 1, 1 pi by 2 3 are 6. So pi by 6, if you do it, you got it as b1 as well. Similarly, if you want to find pi, product of terms, right? What is the value I am substituting in our given transfer function? K is equals to 1 to 3 minus 1. 3 minus 1 is what? 2. 2 by 2 cancel. Only to get 1 term. Here we had 1. Everywhere, wherever K is there, put the 1. So that's the reason we substituted in the given formula. And we can write as B naught by Sn plus C naught. B1 by Sn square plus B1 of Sn plus C1. All the coefficients we substituted. And we can evaluate B naught and B1 by using this relation. What is the relation? When Sn naught is equals to 0. Suppose this is your 0 terms. This and this gets cancelled. We can get B naught B1 0.375 plus 0 into 0.89. If you do this, we can get that factor as 3 into B naught B1. So suppose for example, B naught is equals to B1. Both are equal. What I can write? S of n 3 into B naught B1 naught B naught square. H of s is always 1. Shift there, it will be B naught value we obtain by substituting this value. So wherever B naught is there and B1 is there, we can substitute this given parameter. So till now we obtain of h of Sn. How we got h of Sn? This is our B naught by Sn plus B naught. Here B1 by S1 square plus B1 of Sn plus whatever the coefficient we have. We have both the values, multiply these two. We got 0.329 by Sn cube. If you multiply this factor Sn plus this whole with that term, we can got this as a next factor. Clear? So we have got this factor and we can, now what you need to do now? Critical frequency, right? You have to find critical frequency. Omega C is equals to omega p 0.6 radian per second. Always remember critical frequency and the passband frequency we are assuming as 0.64 and s by 0.64 wherever s is there. If you further simplify, we already have seen the simplification factors for it. If you simplify that further, we can able to write our transfer function h of s with these given parameters. Now what is the next step? As I mentioned, we have to use the bilinear transformation. So we are using bilinear transformation. We are converting h of s into h of z. Transfer function. So now what we are doing? This is s. This is your s square x cube. S is there. Here we are just need to substitute this factor. What is t value, students? T is what? 1 second. So we can replace this t with 1 second. So we can write as 1 minus z power minus 1 by 1 plus z power minus 1. This whole factor we are replacing here. So what is 2 cube, student? 2 cube will become now? It's become 8. What is s now? 1 minus z power minus 1 by 1 plus z power minus 1. Whole power 3 is there. Plus, similarly the second coefficient is as it is. S square is there. 0.4799 into s square. S is what actually? 2. 2 square will be 4, right? Into 1 minus z power minus 1 by 1 plus z power minus 1 whole square. Plus this s value. What is s value now? 0.422 into 2 with the same factor and constant is as it is. So this is the way we replace here. And what we can do it, we have taken 1 plus z power minus 1 whole cube common. So this is what, nothing is there with 8, only a minus b whole cube, a cube minus b cube plus 3ab into a minus b. We substituted that factor. And for the second one, what is that? If you take 1 plus z power minus 1 whole cube common, then here we'll get 1 plus z power minus 1. Not mine. It's not a plus term, students. It's not a negative. It's a plus one. Okay. Similarly, for the last, we can write 1 plus z whole power minus 1 cube. So a cube plus b cube plus 3a square, b plus 3ab square we can write. And for the second factor, we can write down the term as it is. And a 1 plus z, whatever there in the denominator by denominator come in the numerator. And we can write 1 cube plus z power minus 1 cube. So the 1 cube is 1, z power minus 1 whole cube will become z power minus 3 plus 3ab into a plus b. We wrote as it is. So this is how we got the whole term as 0.0862 1 plus z power minus 3 into 3 z power minus 1 is 3 z power minus 1, 3 z power minus 1 z power minus 1, 3 z power minus 2. We got the particular factor. Similarly, if you take 8 and if you multiply with the second factor, what I can write for this? This is 3 as it is. 3 1s are 3, 3 z power minus 1 z power minus 1 is z power minus 2. Clear? Similarly, for the second, 1 1s are 1, z power minus 1 in the second term we can write z power minus 1. Similarly, 2 into z power minus 1, 2 z power minus 1, and z same thing we multiply with 1 as well as with z power minus 1 as well. We got this is our whole expansion. Similarly, for this, we have multiply 1 minus z power minus 1 with this factor a plus b whole square, that is 1 plus z power minus 1 whole square. If you do it, we got the second term as well. Similarly, for the last term, what I can write for it? A plus b whole cube, we have wrote it a cube plus b cube plus 3a square b plus 3ab square. At the end, what I need to do in the denominator, I'll take the like term common, like z power minus 3 is here, in the z power minus 3, in the z power minus 3, and here is also z power minus 3. So what I can get that, here I'll get minus 8, here I'll get minus 1.919 because it's negative. Here also I have negative minus 0.844 is there. Here is what? Plus 0.087. So this, if I'll take common with z power cube, what I get? I got this factors. So now what I'm doing, at the end I'm taking common and further simplifying. So all the things what I'm doing, the same numerator coefficient we are writing as it is, and this is we are keeping as it is. In the denominator we are separately writing, and later on we'll take the later on we'll try to write the coefficient. If you write those coefficients, what is the next term we are going to get? We are going to get the next term as this factor. So same thing, we got constant z power minus 3, z power minus 2 and z power minus 1. At the end, if you multiply 0.806 with 1 0.806 plus 0.8062 z power minus 3 is as it is, 0.806 into 3 will be 0.2586, 0.0862 into 3, the same thing will get 0.2586. This is in numerator. Now, what is the constant I do have in denominator? I had as 10.85. 10.85. So here also, in all the terms, if I divide by 10.85, what I can write? I got as 1 minus 10.676 by 10.85, 18.826 by 10.85, 19.348 by 10.85. If I do with all, I can got this factor in the denominator. Clear? This is the denominator. Numerator is as this. Whatever the terms we do have, we are dividing with 10.85 with all. Like for this term, for second, third and fourth, we can get that answer. This is actual z of z we obtained, students. So this is your h of z, right? This is the transfer function in z domain. Now what is the last step we have to do it? We have to take the realization structure. Means how do we realize that? Is in direct form 1 and direct form 2, both the way we will understand. Direct form 1, h of z is nothing but y of z by x of z. That is called total h of z. Right? So what I am doing, y of z by x of z, if I want to do it, what is the y of z I have? This is the y of z coefficients, numerator. Denominator terms is x of z. Tell me the coefficients here. 0.0079. So we are just plotting the directly here. I'll be drawing the complete structure. we'll just write down here the coefficients that is missing here. What we will write, student, with y x of z? First coefficient is 1.783, should be the first here. 1.783 should be the first one, because the only z power minus 1 is there, no? Similarly for the second here, minus 1.732, because z power minus 1 will become z power minus 2. For the last term, what I can write? 0 minus 0 point, what is there? Minus 0.984, that should be there here. The third block, right? First block, z power 1 into that coefficient, z power minus 1 into z power minus 1. This is our equal part should be added, right? So we need to add the power. So we can write z power minus 1, z power minus 1 as z power minus 2, right? So that's z power minus 2 we are writing, and we just write the coefficient. So I just put a blank so that you can write those values for x of z. X of z is a denominator, right? Y of z is a numerator. Realization with the writing the coefficients here. What is the first coefficient we write? 0.0079 at this numerator end. And the second one, what we do have, 0.0079 at this end with z power minus 3. That means it should be at the end, right? At this particular value. Because z power minus 1, z power minus 1, z power minus 1 total will be z power minus 3. So we have written that way the value for it. Similarly, what is the next value we do have, students? So we can write it down. The next value for this coefficient, z power minus 1, 0.023 will be there at this particular point, and 0.0023 at this particular point, and 0.0079 at the end, and similarly for the first as well. With all the values, we can write this z power coefficients, and we can able to write the answer for it. Clear? Similarly, next thing for the second model, if you want to design it, filter design using the Butterworth approximation technique. If you want to do it that one, that also can be analyzed by using the same formula. In this, what we need to understand, how it is going to work, what are the things it's going to comprise of, everything we can understand by using that particular technique, right? So what is the first technique we have to see, students? The first technique is regarding low pass, then next is high pass, then is the band pass. Band pass means it only allows a certain band. So below this omega c it won't allow, above this omega c it won't allow. Omega c1 and omega c2. Likewise, omega 1 and omega 2. Omega L is nothing but lower component frequency. Omega H is nothing but the higher component frequency. This is for normalized diagram for our given whatever the things it's giving to go get that one from the Butterworth approximation we can able to find out. Similarly, the normalized low pass filter design prototype, how do we going to get that? That also going to obtain by using this relation. So omega p is equals to this one. What is this? Omega 1, right? This is a higher frequency, right? Pass band frequency. Similarly, omega 2 is nothing but this stop band frequency. If you see both the things into consideration, if you see that one as this one, that is nothing but 1 radian per second. How do we obtain the equation for that? So to get the relative value minimum of what is A and B, means out of this consideration, if you just want to see how it is going to obtain normalized and unnormalized prototype of that one, we can understand by using its relative frequency. So that is what we can use it, and we can design as well. Clear? But as per this diagram, how many frequencies we do have, students? We had in the previous one for band pass filter, it is 4 types of omega 1, omega 2. There are 2 critical frequencies, omega L and omega H. They are that one. Lower component and higher component or upper component. Omega U also we can write. The meaning is the same only. Next thing, how we design that one. What are the steps we need to understand? First step is we have to calculate all these values. Omega 1 lower component frequency, omega U upper component, and omega 2 using either bilinear transformation or impulse invariant techniques. Impulse invariant techniques we can use it. Next thing, step 2, we always have to assume omega p is equals to 1 radian per second. We have to find relative omega s. We have to find. How do we get relative velocity for that? Relative frequency minimum of A and B, where A is what? Minus omega 1 square plus omega L and omega U into omega 1 into omega U minus omega L. If you want to find B, omega 2 square minus, instead of plus here you have to put B minus. That's it. That's the difference. Here minus omega 1 square, here plus omega 2, because lower, right? Lower starting with negative, higher ending with positive. we can find A as well as B. We can able to find their answer for it. Clear? So this is how we can able to obtain that particular answer for that given kind of transformation. We can substitute and we can able to find their respective answer. That's the step 2. Then step 3, find the normalized transfer function by using the same order. If it is for Chebyshev, if it is for Butterworth, we know both the formula, right? N is equals to log of given term 1 minus AP square minus 1 by 1 minus A square minus 1 whole power 1 by 2 log by omega S by omega P. That is there for log for Butterworth. For Chebyshev, what is there? Cos H inverse of same formula 1 by A square minus 1 by 1 by AP square minus 1 whole power 1 by 2 by cos H inverse of omega S by omega P. Next step is what? Compute the digital transfer function h of z either using bilinear or impulse invariant techniques. We have to compute that as well. Next step, realize the structures. How do we get the structures? Because structures are more important for designing as well as for analyzing. We have to keep in our eye that how do we design the structures. That designing can be done by using direct form 1 and direct form 2. Clear? So they may give you band pass filter for Butterworth. So let us see one problem. How do we get that? So using bilinear transformation technique, design a digital band pass filter. Butterworth, by using which technique we are using? Bilinear transformation techniques, and by using the Butterworth with the following specification. They gave Fs means what is Fs? Frequency in the stop band 8 kilohertz. It is in hertz, students. What you have to do? You have to convert into radians per second, right? Till now, whatever problem we have done, we have seen it's given radian per sample. Now this is the question in which it's given kilohertz. Next one, they gave alpha D decibel. It is given in decibel 2 dB, and the frequency is given for that is omega 1 and omega 2. It's 800 hertz to 1000 hertz. And alpha S. This is alpha P. This is alpha S, right? The range is also given for that. Range also can be obtained by using that particular transformation, right? So this is the range that is given. First thing we have to find T, right? Time period is not given. But what is the sample frequency? Fs. It's not stop band, students. I'm sorry. It's sampling. Sampling frequency 1 by Fs, right? Time period is not reverse the frequency. So 0.125 millisecond is the frequency. We got T. We have taken in terms of time. F1 is given as what? 800. This one is there. F1 is this lower frequency. FL is what? 800. FU upper frequency is 1000. F2 is given as what? This F2 value 800, 1000. This is 400, right? F2 will be the given specification will be always try to find F2 will be higher than that one. So here is F2, right? 2000 hertz. So that's what F2. Next one, finding omega 1 because it is in what? It is in hertz, right? We have to convert in radian per second. So for that, we have to write 2 pi f by fs. So we'll divide it. 2 pi f1 is your 400 by fs is how much? 8 kilo. That is 8000. If you do it, it will be 0.1 pi. FL, what is FL? 8000. Sorry, 800 by fs is what? 8000. So 8 cancel. Will be 10 left here in the denominator. So 2 by 10 is 0.2 pi. Likewise, omega u. Omega u is what? Digital frequency. These are digital, right? We have to convert into analog later on. So what is 2 pi fu? What is fu? 1000 divided by fs. What is fs? Sampling frequency a into 10 power 3. That is 8000, right? If you do it, fu. What is fu? 1000. So 2 into 1000 by 8000. So 2 to 1000 cancel. 2 into 1 by 8. So 2 by 8 is 1 by 4. 1 by 4 is 0.25. Omega 2, 2000. So 2 into 2000 is 4000 by 8000. 1 by 2. 1 by 2 is something for 0.5. 0.5 pi radian per sample. This all are in sample, right? We have to write in seconds. So what we were doing, we are using the same formula. 2 by t tan of omega 1 by 2. What is t now? Milli, right? 0.125 milli. So same thing we substitute in all omega 1, omega L, omega u and omega 2. If you substitute all the values starting from the ending, omega 1 to omega L, omega u to omega 2. If you substitute all the values, we can find all the answers for it. Clear? Till now we found the frequency. Next thing, we have to find A and B, no? A also minus omega 1 square plus, we just now learned this formula. You have to note it down all these concepts. A is we got this one, B we got this one. If you have A and B, both the values, we can substitute in the given formula. This is the formula omega 1. We had 2.5k, that is 2534 radian per second. So that we put it, if you do the square of it, plus omega L and omega U. So what is omega L we had? Omega L is 519 into omega U 6627. That we multiply divided by omega 1 into this. If you know simplify this one, values are there above. Only you have to substitute and you have to find. We substitute all, we get A as well as B. Then we have to find omega S, that is minimum of A and B. Which is the minimum? 7.739 is obviously minimum out of 9.69. So we took it as 7.739 radian per second is for the stop band frequency. Clear? We obtain now stop band. Next, students, right? So how do we obtain AS NAP? We can have AS is this, NAP is this one. The continuation of these all problem, it's a lengthy one. We will try to solve in the next session. Okay? Thank you so much. Hope that everyone is fine. Take care of yourself. Be safe. Have a great day. Goodbye.